What's up, everyone? This is a video lesson for 9.2, and here you're going to be introduced to a logarithm. All right. I actually want you to start off. You're already watching this video, but I actually want you to watch another video as well. So in your notes, the numbers file, you can click this link that says video intro, and it'll lead you to a video that kind of briefly discusses what a logarithm is. Okay, so I want you to take a few minutes to watch that, and then you can come back to this video and you can pick up from there, okay? Now, a logarithmic function, it's simply the inverse of an exponential function, okay? And it's been a little while since we talked about how to find the inverse of something, but just recall to do so, you just simply need to switch the position of x and y in your equation, okay? So if we're working with an exponential equation of y equals a to the power of x, to find its inverse, we simply need to make this become x equals a to the power of y, okay? Now, the issue here is since y is within the exponent now, it's challenging, it's difficult for us to solve this back for y, all right? So this leads us into what's considered a logarithmic form, okay? X equals a to the power of y is equivalent to log base a of x equals y, all right? Log base a of x equals y, all right? So this is known as a logarithm, okay? X equals a to the power of y, we would consider that the exponential form of this inverse, and then log base a of x equals y is the logarithmic form of this inverse, all right? Now some stipulations here. Both a and x, they have to be positive values. They both have to be greater than 0. And then what I really want you to understand more than anything is y here represents an exponent, right, in this inverse. So that means that a logarithm is just a fancy way of representing an exponent, okay? Quicker you wrap your head around that, the better off you'll be. All right, so the first thing we want to do is just be able to convert back and forth between exponential and logarithmic forms of these guys, okay? So log base 3 of 9 equals 2. That's, of course, considered logarithmic form. To put it in exponential form, I start with the base of the logarithm, which is just this little subscript of 3. I take that 3, I raise it to the power of 2, and then that equals the argument of the logarithm, which is 9. Okay, so 3 squared equals 9 is your exponential form. All right, then we have log of 1/100th equals -2. First thing I want you to notice here is that that logarithm does not have a base written for it. So this is actually understood to be a common logarithm, which has a base of 10. And these are logarithms where you don't write that base. It's just understood that there's technically a 10 here, okay? So to put this in exponential form, I take that base of 10, I raise it to the power of -2, and then that equals the argument of 1/100th. Okay, let's go in the other direction. Write each equation in logarithmic form. 5 to the third power equals 125. So the base of this equation is 5. That means the base of the logarithm needs to be 5. So again, I start with that base. I take log base 5 of 125 equals the exponent of 3. Okay. Similarly, 27 to the 1/3 power equals 3. I start with the base of 27, take log base 27 of 3 equals 1/3. Okay. All right, moving forward. Evaluate each expression here. Log base 3 of 243, what does that equal? So I think it's important to understand that logarithms can just represent numerical values, all right? So what I'm saying here is 3 raised to what power equals 243. If you think of this as like in its exponential form, okay? And of course, the answer here is 5, right? Because 243 is the same as 3 to the 5th power, okay? How about log base 2 of 1/16? So 2 to what power is 1/16, right? 1/16 can be thought of as 2 to the -4th power. So in the end, this logarithm equals -4. Okay. And then lastly, log of -100. This is log base 10 of -100. This is a common logarithm here. So we're saying 10 to what power equals -100? Well, that's not possible. Whenever you raise 10 to a power, whether the power is positive or negative, the result is always going to be larger than 0, all right? So that means this logarithm, we're going to say, is undefined. And this is an example to help you see. Recall when we introduced the logarithm a couple slides back, we said that a and y, they have to be positive values if the logarithm's in this form. So in this case, we have our argument here of the logarithm. It's negative, so that's violating the rules of a logarithm. Okay. All right, moving forward. Now we have some logarithmic equations to solve. I have log base 8 of n equals 4/3. Put it in its exponential form. 8 to the power of 4/3 is equal to n. This is a good review of how to handle rational exponents. Recall this can be rewritten as the cube root of 8 to the 4th power. We know the cube root of 8 is, of course, 2. 2 to the 4th is 16. All right. How about log base 16 of x equals 5/2? So we have 16 to the power of 5/2 is equal to x in the exponential form. 16 to the power of 5/2, that's the same as the square root of 16 raised to the 5th power. Okay. And of course, we know the square root of 16 is 4. And then 4 to the 5th power is 1024. Okay. All right, your turn to practice. I want you to pause the video and try the problems that are on practice 1 here, and then check your work with mine. All right, we're going to finish up with some logarithmic equations and inequalities. So we have a property of equality for logarithmic functions that says if log base a of m is equal to log base a of n, then that means the arguments of those logarithms have to be equal to each other. M has to equal n. So that's only going to work if the two logarithms have the same base. All right. So we can apply that to this equation. I have log base 3 of x squared minus 15 equals log base 3 of 2x. So the fact that both of those logarithms have the same base of 3 means that x squared minus 15 can equal 2x. And then I have to solve this quadratic equation. All right. I can do so by factoring. This factors to x minus 5, x plus 3. So I end up with x equaling 5 and -3. Okay. Notice the directions say to check my solutions, though. And the reason for that is if our solutions, when we plug them back into either argument, if they make the argument simplify to a negative number, then you have to rule them out. Okay. When I plug 5 back in to either argument, I'm going to end up with 10 as the simplified argument. So that's okay. That's positive. But if I plug -3 back in, that's going to lead me to an argument that is -6, okay? And that logarithm would not be defined in that case. So I need to exclude the value of -3 that I came up with and only keep 5 as my solution, okay? All right, final example here. Now we're looking at a logarithmic inequality. And this requires a little bit more work because there are an infinite amount of values that could be extraneous when you try to solve an inequality, okay? So the first thing we want to do here, provided that the logarithms have the same base, we want to begin by finding domain restrictions on each of the arguments, okay? So I'm going to set the argument of 2x plus 1 greater than 0, and the same with x plus 4. Again, just because the arguments have to be positive values. All right, so that means x could be greater than -1/2 for the first logarithm, and x has to be greater than -4 for the second logarithm, okay? From there, I'm going to solve just the inequality of 2x plus 1 is less than x plus 4. So now I'm taking the arguments and bringing the inequality itself into play. Okay, so if I solve that, I'll just end up with x is less than 3. All right, so if I just kept the solution as x is less than 3, I would be including numbers in my solution set that would violate these domain restrictions, okay? And they would make the logarithms on either side of this inequality undefined. So I essentially need to formulate a solution by using the restrictions from part A along with what I came up with in part B. And what it really comes down to is looking for the overlap between the three, okay? So just draw out a number line here. Doesn't have to be real sophisticated. We're going to place -4, -1/2, and then +3 on there. And of course, x is greater than 1/2 would graph to look like this. X is greater than -4 would look like this. And then x is less than 3 would look like this. And again, we're just trying to find the overlap of all three of those, which is right in here between -1/2 and 3. So I'm going to say my final solution spans from -1/2 up to +3.